Welcome back to the lecture. We continue from what was there in the last lecture on the Heisenberg's uncertainty principle, and I introduced a simple quantity called the average value or the expectation value. So, in this part of the lecture we will consider the formal definition for expectation values in quantum mechanics, and if time permits I shall talk more about the postulatory basis, that is basis with which mathematically we can start that these are the starting points and then quantum mechanics we can build. That is called the postulatory basis, and the postulatory basis in quantum mechanics will also be stated in very simple terms. The postulates are mathematical in nature, but we will see simple explanations hopefully. Okay. First one is the expectation value. It is denoted by the average value bracket for any quantity. The average value is in general calculated according to the standard prescription that if there are n measurements and these things happen with different outcomes for the measured quantity A with values A1, A2, AN for different measurements, then you know that the average is nothing but the sum over I is equal to 1 to n AI divided by n. Now on the other hand, suppose you have A1 occurring n1 times in an experiment repeated many times, A2 occurring n2 times. Let me change n1 n2 to something else which is standard. Okay. P1 times P2 times, and likewise AN, and these are the only possible values. Let us say these are the only outcomes that you have, occurs Pn times. Then the average is calculated by adding all the A1. So the average is calculated by adding all the A1 P1 times and adding A2 which has happened P2 times, and likewise adding all the ANs which have occurred Pn times, dividing by P1, P2, P3 up to Pn. Okay. This is also the standard way in which you can calculate the averages. If some values repeat many times, then you want to find out how many times that it has repeated, what is the probability that that value is repeated, and so on. Now the same thing can now be written by writing A1 into P1 by P, okay, where P is the sum of all of the experiments Pi, and therefore P1 by P gives you the probability that you got A1 for the measurement of A, and likewise A2 into P2 by P, which is the probability that you have the outcome A2 and so on. Therefore you have AN Pn by P. Okay. So this is a probability within brackets that a given value occurs, and then what is the average when you do this experiment many times. This is a standard way of representing probabilities, and in quantum mechanics you remember psi star psi represents the probability density for the system at a given coordinate or at a given momentum, the variable x. In particular in the one dimensional box, you talk about the psi star psi dx as the probability that the system is in the space between x and x plus dx. And in 2 dimensions, psi star psi dx dy talks about the probability that the system is in the area dx dy, which is enclosed between x and x plus dx and y plus dy. That is what it is. And therefore, psi star psi is a sort of a probability, and then what you have is the measured value, whatever that you measure the energy or you measure the position, you measure the momentum, it does not matter, some experimentally observable quantity for which there is an operator associated with it in quantum mechanics. The measured value gives you the value with that probability, and then the average value is the sum of all of those things. The measured value times the probability that it happens summed over all such possible measured values. Therefore, technically if you are looking at A as a function of x, because please remember this is a continuous function, therefore A is defined for each and every value of x. So what you think is, it's like psi star psi, which is the probability, times the value Ax that happens at x dx, provided psi star psi represents the probability density, which means this integral psi star psi dx should be equal to 1, okay, should be equal to 1. So if you represent this by probability density in quantum mechanics, the average value A is the probability times the value that happens with that probability summed over, but with one small technical difference, namely that the operator corresponding to A acting on psi giving you the measured value, and therefore the measured value times the psi star psi is represented by this quantity divided by integral psi star psi dx, which of course is set to 1 if we think of psi star psi as the probability. So this is the formal definition for the expectation value, and this A is the operator associated with the measured quantity, the physical property called A. This is the physical property, and this quantity is the mathematical representation or a quantum mechanical representation of that physical property. Okay. You already know, because the case of momentum, for example, the operator associated with P is minus h bar d by dx for one dimension, and what is the operator for the position? It is just the x itself. What is the operator for the energy? You have already seen that it is the Hamiltonian operator. What is the operator associated with angular momentum? It is a vector and has 3 components in 3 dimensions or in n components in n dimensions. So if you write that in say 3 dimensions, you have 3 components, and each one of them is represented by a corresponding operator, which is slightly different from the notation that we have here. It will involve the derivatives. So the point is, every measured quantity has a mathematical representation in quantum mechanics, and the average value that we expect, by definition the average being the average of an infinitely large number of measurements, the average value that we expect for that system that you see here, the average value is the psi star operator psi dx. This is a fundamentally important thing to remember, and again when we introduce the postulates of quantum mechanics, this will be introduced as one of the postulates of quantum mechanics itself. Therefore, in the last lecture when I said that the average value of the position logically turns out to be somewhere right in the middle of the box for a box of length L, you can calculate for one dimension the average value x to be psi n of x. If the state of the system is psi n, then the average value in that state is psi n of x, the position operator x, and psi n of x dx. And psi n being normalized to root 2 by L, whatever you have, that is root 2 by L times sin n pi x by L, you have for the integral 0 to L sin n pi x by L x sin n pi x by L dx. Okay. So, this gives you, when you do the integral, this gives you the answer L by 2. It's a very simple integral. It is x sin square x, and sin square x is, of course, you can write it as 1 minus cos 2x by 2, and then you do the simple integral on x and x cos x. It's very easy to do. Likewise, the average value for the momentum for the particle was also argued out to be 0 based on the fact that the momentum is a vector and therefore it has a positive or a definite negative direction at any point in space. If you do that, the average value of the momentum will turn out to be 0 for the particle in a one dimensional box, and that is also easy to verify by writing this down as 2 by L sin n pi x by L. Now you remember to put the operator in the middle, IH bar d by dx sin n pi x by L times dx. Now the derivative of the sine will give you a cosine n pi x by L, you can see mathematically, and the sine cosine will give you a sine 2 n pi x by L times 1 by 2, but that integral between 0 to L is a full sine wave, and therefore that goes to 0, okay, dx. So it's easy to verify simple relations like the expectation values for position, expectation values for momentum, and these are the two things that you can think about. And if you have the kinetic energy, you already know that the particle in the box has only kinetic energy inside the box. Therefore, the total energy is the same as that of the kinetic energy, and you can see that the average value E for the particle in the state psi n is h square n square by 8 ml square. That also comes out. So, these are simple prescriptions for doing calculations for the average values based on quantum mechanics. Now, please remember, these are average values. Expectation values, that is, these are what are expected when you do many measurements. But if I do a single experiment, what value will I get? Is there a prescription in quantum mechanics? That's what this equation tells you. Okay. If the state of the system is in this function, is in this state psi n for the particle in the one dimensional box, it does not matter how many times I make measurements on that state for the energy does not matter, all the times I will get only one answer, namely E n psi n of x. It is like the simple analogy, you have a die with 6 faces and you print only one dot on all the 6 faces. Therefore, the die has only one state, namely with an outcome of a single dot. No matter how many times you throw the die, you get only one dot as the answer, because that is how you prepared the state of the system. Such states are called eigenstates in quantum mechanics. Okay. In the case of a die, you have 6 possible things that you have for a single die: 1 dot, 2 dot, 3 dot, 4 dot, 5 dot, and 6 dots. Therefore, you have 6 possible outcomes. In the case of a particle in a box, if I make a measurement and I do not know what the state of the system is, what result can I expect for a single measurement? I have already told you what result we can expect for a very large number of measurements, and then what is the average. That is what we did before. What is it for a single measurement? If you ask that question, the answer is one of the eigenvalues of the system. In case of the die, which is a normal die or a regular die, which has 6 different phases with 1, 2, 3, 4, 5, 6 dots, there are 6 possible outcomes, multiple outcomes. Therefore, in a single experiment of throwing the die, we get a dot or 2 dot or 3 dot, all with identical probabilities 1 by 6 if the die is a perfect cube, because the die is not prepared in any other way. Likewise, in quantum mechanics, if the probabilities for all outcomes are uniform, then in a single measurement, one of these energies will be the outcome. For the particle in a box, if you measure the energy, only one of the ENs is possible. Which of the EN? Statistics. Einstein was very unhappy. He said God doesn't play dice, and Niels Bohr told him, don't tell God what to do. Okay. But there is an inherent statistical character built in the measurement outcomes according to what is called the Copenhagen school or the Niels Bohr school of quantum mechanics, which is still practiced by most of us. A single measurement will give you one of the eigenvalues and will result in the state of the system being one of that eigenstate, the eigenstate corresponding to that eigenvalue. Therefore, if we make a measurement for a particle in a one-dimensional box in an arbitrary state that we do not know what it is, the result that we will get out is only one result, and that result, the measurement will give you an eigenvalue En, and the state of the system will become psi n. This is fundamental in quantum mechanics, and if the state is already an eigenstate, then no matter how many times you make copies of that state and how many times you make the measurements, you will always get the eigenvalue. That is why I wrote the average value for E in the last slide, or a few minutes ago. If I go back to the screen, I have written that already here. If the state of the system is psi n, the measurement of energy every time will give you the same value, h square n square by 8 ml square, and since it is the same value in all measurements, the average is also the same as the single measurement. If you know the state of the system very precisely, that is what it is. If you do not know the state of the system to be an eigenstate but an arbitrary psi, okay, this is the result. For an arbitrary psi, now let me write down the tab psi here, that if the system is in the state psi, a measurement of a quantity physically will give you psi star a psi dx integrated over the domains completely available to the system, and for particle in a one dimensional box it is between 0 to L. That is the whole space available to the system. Therefore, you take the average by adding all the probabilities. It is very easy to see that the same one is what you get, because if you write E of psi n, which is an eigenstate of the Hamiltonian operator, then you see that this relation is psi n h psi n dx, and you know between 0 to L, you know that h psi n is E n psi n, and you know that psi n is normalized. Therefore, the answer is 0 to L psi n dx, and with E n, and this is equal to 1, and therefore the average value is the same as the eigenvalue for E n. Let me stop here, and we will continue these discussions over the next few weeks on various aspects. but it's important for us to remember that the expectation value is a fundamentally important quantity, and the fact that that involves a wave function and its complex conjugate is a very meaningful reason, is a very important reason why one is always interested in solving the Schrodinger equation to get the wave function first. That the wave function has an interpretation due to probability is one thing, but the wave function is extremely important in the actual calculation for the expectation values and the measurements, and therefore you have a function which you cannot physically explain or visualize, but it's very important and very useful for calculating average values, as calculating other quantities called matrix elements, calculating the average values through various processes and so on. Therefore, the wave function has come to stay with all of us. We'll continue this in the next lecture. Thank you.